So my name's Jim, and I work at Neo4j as Chief Scientist. And today I want to talk a little bit about where we're going in the world of graph technology, in the world of technology that's built purposely for graphs, which we've sort of named Graph Native. And what we'll talk about today is hopefully an entertaining mixture of stuff. I'm going to give you a little talk about what I mean by Graph Native, an overview of Graph Native tech. We'll do a cheeky little bit of computer science. Don't worry, nothing too onerous, kind of algorithms 101 level computer science to see how our implementation choices can shape what we can do with the kind of technology we're working with. I'll then take a look at some database architecture from 30,000 feet and contrast some competing approaches towards building graph technology and see how those pros and cons shake out. I'm particularly then going to contrast that with the way we build Neo4j and hope to demonstrate that the way we build Neo4j makes it an excellent choice for graph workloads. I'll try to reinforce some of that by giving you some quantitative data. So we have some interesting performance numbers and some reliability characteristics, which is why we think building 4 graphs from the ground up is a good idea. And then as Corey mentioned, towards the end, we'll do a bit of Q&A and give you guys a chance to voice your questions. So that being said, let me say there are some assumptions that I work on. I think that graphs are the most important data structure on the planet. I also think that throughout my career, even outside of my career at Neo, that many of the workloads, many of the data modeling challenges that I encountered could have been conveniently modeled as graphs. And I think now that many, if not most, workloads are conveniently modeled and executed as graph queries, graph computation. So that's my assumption, that graphs are fundamentally important and therefore they are worthy of their own technical category and their own unique and discrete technological choices. So let's start some of this. We do a little bit of science. Sadly, as I age, I find I'm looking increasingly like Hubert Farnsworth here. But we're going to do a little bit of computer science, and I'd like you to recall back to, for those of you that did computer science or computer engineering, if you recall your algorithms 101 class or moral equivalent where you were. And I'd like to introduce you to or reintroduce you hopefully to an unordered singly linked list. Okay, sort of a basic level data structure. But what are the properties of this list? Actually, this list has some really interesting properties, one of which is it imposes a total ordering. And for those of us who work in distributed systems, that's always very useful. But actually, the properties of this list are if you want to add something, it's super easy. You just bolt it onto the beginning of the list, and then it's added. The flip side is it's kind of it's a bit rubbish for finding things in an unordered list, that you have to chain through the whole of the list to find if a value is in there or if a value isn't in there. And if you remember from algorithms class, we say therefore that we can write to this list in O1 in constant time. It's the cheapest possible costing for an operation. No matter how many items there are in that list, I can always add another one at the same cheap cost. Conversely, we say that the reading the list, finding a value in the list is ON, because as the size of the list grows, it takes more steps for me to find a value or determine that a value isn't present in that list. Now that's a pretty basic data structure, right? I don't think anyone struggles with that. But even those basic data structures have useful properties that we can use. In fact, there are even some parts of Neo4j that use linked lists primarily around their write performance. So in a way, you could put a box around it, you could drop an API on it, and you could quite legitimately, if somewhat humorously, call this a write-centric database. Voila, the box says it's a database. I put a PowerPoint arrow on it to give it architectural authenticity. And now what we have here is a write-centric database. A database that's not terribly good for reads, but is potentially very good for uncontended writes. Works great for one client, but of course, when we have many clients, we have the problem that each of these clients contends for access to the head or tail of that list, depending on where we're going to insert things. So it's not great, perhaps, for a multi-threaded database. However, computer scientists as we are for the moment, we have ways of getting around that. We have things like conflict-free replicated data types, CRDTs, which would allow each client to work on a copy of its own list and then merge those lists together into some super list. In fact, this is really great as a CRDT because the ultimate list is unordered. There aren't any complex merge rules or anything we have to apply. So now we can have a database which is good for multiple client writes. So we have a very multi-threaded friendly, multi-client friendly write-centric database, which still sucks for reads. Of course, you can do all kinds of fun stuff here. I mean, this basic pattern you could do with an off-the-shelf CRDT library, but you've got a whole bunch of other options here. You could do like the Disruptor guys did, the LMAX trading guys did, and have an enormous ring buffer that you write into, do your concurrency control outside of the kernel, so it's super, super fast and so on. So there are some mechanical things on top of this computer science you can do to get even higher performance right into this system. But this is still an expensive database, in quotes, to read from. So next we can move on to trees. Trees being generally the next structure we learn in CS 101. So if I was to go ahead and insert a bunch of values from the bottom right corner into this trivial binary tree, I end up with this kind of structure. And the lovely thing about trees, this is a simple binary tree. More sophisticated trees do exist, and we'll talk about them shortly. But the lovely thing about trees is that reading from a tree is typically log n of the number of items in the tree, and that's a nice property, right, compared to order n. Growing complexity at logarithmic of the number of elements means it's a lot cheaper for larger data structures. So if I had a list of size 1 million, then typically I'm going to have to read 1 million or so elements before I can find the thing I'm interested in or find that it doesn't exist. But at scale 1 million, I might only need to examine 6 elements of a tree to find the element I want or discover that it doesn't exist. That's a lot cheaper. And given that many of the many realistic production databases don't have millions, but perhaps billions of items, that saving of going from billions of record examinations down to 9 is actually very welcome. And another lovely property about trees is that you can spread contention. Compared to the list, where you could only write, in my example, at the tail, using a tree allows us to spread contention around. So we can have clients writing all across the leading edge of the tree and minimizing mechanical aspects like lock contention that you typically have. Of course, this isn't a free lunch, and actually our trees mean that what we're getting in terms of read benefits, we have to pay for on the write channel. So now our writes, far from being constant time order 1 writes, from the list point of view, they are now, again, also order log n writes, because you have to first read to the point in the tree where you want to insert and then do an O1 operation to insert. So there's an interesting trade-off there, I think, between even those kind of simplistic structures that we all know from our computer science backgrounds. Now, of course, databases usually love trees. We've all studied databases perhaps at university, or if you're interested in databases because you're on this webinar, you'll know that so many classic database implementations are based on B trees. So the arrangement typically is that you host your index in your fast RAM, and then potentially you have your actual records of perhaps the rows in your table on secondary storage on disk, and a B tree fits that very nicely. It gives you that logarithmic lookup performance in your index, while meaning that you only have to go to disk occasionally when you found the record you want to retrieve. But occasionally, even those trees have pathological issues where you end up rebalancing. So, of course, if you need to keep your tree at some balanced level, there may well be a blocking expensive operation that needs to happen periodically to do the housekeeping over your tree. So, really, and what I'm trying to convey is that there's no such thing as a free lunch. Now, at this point, you might be thinking, so what, Jim? I'm a user of a database. I've got a day job to do. Why are you reminding me about these algorithms lectures, which are alternately awful and snoozeful? Well, I think the reason I'm saying you is that even with this simple tree versus list comparison, is that you have to choose the data structures for your workload quite carefully. The implementation will empower you for some cases. So in the list case, you're empowered to do perhaps high performance writes and inhibit you in others. So again, on that list case, it was pretty poor for reads. So a B-tree index database might be a good idea for a relational database or perhaps for a document database. A hash ring might be great for columns, but none of those approaches are typically very good for graphs, where we need to be sympathetic to the kind of locality and access patterns that graphs engender. So we have to pick the right tool for the right job. Ultimately, if you hammer away at this screw long enough, you can declare that you've got yourself a multi-model screwdriver. But I think this is hardly ideal. I'd like to think about now how that translates into more sophisticated tools, and specifically around graph databases. So it's my contention that all databases have a native model. We have relational databases, you have column stores, you have key value stores, you have document stores, and those things got their names because that's their native model. That's what they're good at. And I think out in the market now, there are several good databases around that each uphold one of those models. However, I also noticed that graphs are becoming extremely important, which is actually quite gladdening to me. I think it's really nice that the world is coming to see that graphs are probably the most important data structure. And now there's a bit of a gold rush on to see who can retrofit graph into their other database quickly and then achieve perhaps tick box parity with a native graph database. I'm going to say I believe that some vendors have simply spotted the enormous market opportunity that graphs have and are jumping on the bandwagon. And in particular, I see two approaches to doing this retrofit operation, two non-native approaches to graph. One is on the left, where you take an existing data store, like a relational store or a column store or something, and then you bolt on some third-party graph API, write some mapping code between that API and the semantics of your store, and then declare victory. The one on the right is where you take an existing data store and you add some additional operators into your query language and then declare victory. Actually, I don't think either of these is tremendously satisfactory. I don't think they give graphs sufficient gravitas. And let's take a look at the architecture, and I hope to explain why that is. So here we see obviously a 30,000-foot view of some of those architectures. On the graph layer approach, we've got the graph API, and we have a graph layer that maps between that graph API and some other database management system, a column store, relational store typically. On the right-hand side, we see the graph operator approach, where you've got an existing query language and you home some graph operator inside that query language. And then it makes use of what the underlying DBMS provides, typically a document store, and uses some kind of user-level constructs, some user-level affordances in order to be able to sort of reify graph out of another non-graph data store. Well, actually, there are a few issues with this. Firstly, at the topmost layer, there's no cipher. And I'm super biased about Cypher. Obviously, I work at Neo4j, and Neo4j first birthed Cypher some years ago before it went on its journey under OpenCypher to become an open standard. But Cypher is the big game in graphs, right? Cypher is probably deployed on 80% of the graph technology out there worldwide, on Neo4j, on Apache Spark, on several other databases that are out there, from including some of the prestigious players. Having no Cypher there effectively locks you out from an extremely rich ecosystem of developer talent and tooling, which makes this approach actually less valuable than it would have otherwise been. In the kind of middle tier, on the left-hand side, we find that the graph layer does a bunch of denormalization. It kind of tries to mask the semantic differences from the underlying database. When doing that denormalization, you make some design choices. Typically, we've seen that people make design choices so that queries up to depth 3, so friend of friend of friend, are relatively inexpensive, but that beyond that level of denormalization, your queries may fall off a cliff edge. And this is driven by common social networking problems. We know from Facebook, for example, that we're all less than 4 hops away from one another approximately. However, I think it gives short change to those other much more interesting and prevalent problems that we have around modeling data centers, or modeling navigation along roads, or modeling healthcare records and clinical pathways, or modeling Mars missions if you're NASA, which actually have depth hop requirements far in excess of 3. In fact, later on I'll show you that a typical, uncontroversial enterprise app will have hop requirements of modest double digits. If you denormalize to favor 3, then 4 is your nemesis. Typically, on the right-hand side, you now need some kind of convention that ties together the graph operator with the underlying data in, like, your document database or whatever. This means if your users don't uphold that convention, bits of your data, which you perhaps like to be in your graph, don't appear to be consumable by your graph operator. And then the reason for that is, of course, that the database management system doesn't really know about graphs. It's a document database, for example. And so it's only by convention that these things hang together. And effectively what the graph operator is a bit of syntactic sugar on top of the existing query planner. It's a little bit tick box. And of course, at the lowest level, at the most fundamental level, neither of these two otherwise competent database management systems understand graphs. So they can't prevent things like dangling relationships. They can't prevent things like logical corruptions happening, simply because they don't know how to process their constraints. Those engines are finely tuned for a completely different workload. They're not native to graph. So here's a bit of Japanese knotweed. It's beautiful, and if you're in Japan, it's native. If you live in the United Kingdom, or I do, it's non-native and actually considered a pest. In the graph layer approach, it suffers because most of the data store is focused on the existing data model, so columns, for example, and the underlying store formats, the way that data is persisted on disk, also designed for that columnar access pattern. Now, a popular implementation, column store, of course, provides a nested hash map structure, so that's the hash map of hash maps. But a hash map does quite the opposite to what we want in graph world. In column world, hash maps make a bunch of sense because you want to spread the data uniformly around your system. And a good hash function will, of course, achieve that. It will try to avoid clashes. However, in graph world, we actually benefit a great deal from having subgraph or neighborhood data co-located in the same memory space. So a hash map in this case actually works against us. It kind of flings data around, whereas actually we'd like data to be co-located. Although the hash map has good theoretical algorithmic performance, so O1 in a good case, in practice having to do a bunch of hash map lookups over the network all adds up. This typically ends in poor performance at relatively modest depth searches, greater than 3, where we haven't denormalized. Gives us schema rigidity because the underlying column store demands a schema which ultimately manifests itself as a graph that can't evolve conveniently, and ultimately difficult evolution. That's not to say column stores are bad. Of course they're not. Column stores are brilliant. They're brilliant for what they're native at, which is columnar data. This is a piece of Himalayan balsam. Again, a beautiful plant, I think, but non-native to where I live in the UK. If you take a graph lookup operator and bolt it into the query language, and then use conventions in the existing model to infer linkage that the operator can use, it means that you haven't got native support for those links, which typically means they're slow. You're not certainly doing O1 lookups. You're probably doing something like log n lookups inside your B-tree index. So we know document databases out there that are competent document databases, and they use B-tree indexes for their query and processing. We know a lot about how B-trees work. We don't know why they're called B-trees, by the way. We don't know if it means balanced. We don't know if it means Boeing, where they were invented. We don't know if it's Bayer who invented it, but we do know a lot about how they work. B-trees, we know, will allow us to give us this nice semantic where the index typically persists in fast RAM, but we also know that it's got log characteristics. So if I was going to traverse a graph by repeatedly looking up a document, teasing out a link from that document, resolving that link in the index, each one of those resolutions may be a log n in cost, where n is the number of documents stored. If I then have to do m of those in order to traverse across my graph, I've got an m log n cost to doing any graph traversal. Of course, you can denormalize and add all sorts of other fancy indexes in, but when you denormalize, you add complexity, and you always have to choose to what extent you denormalize. So, for example, do you denormalize to depth 3? That seems to be pretty common in these kind of things. So this ultimately results in a modest search, poor performance at modest search depth, difficult governance, again, because the underlying engine doesn't respect those links. And actually, since you don't really have a good graph vocabulary at your disposal, you have a graph lookup operator, for example, you can't really express any sophisticated things that you really want to do with the graph. And ultimately, I'm going to advocate again that you pick the right tool for the job. Neo4j is the shaver in this case. It does one thing and does it well. It's designed to do graphs and do it well. If you decide that you're going to build a database for one domain and then shoehorn functionality from another domain on top of it, I mean, frankly, I think you do have to pick your battles. You're going to be good for one, and you're probably going to be far less good for others. And we see this all the time at Neo. So qualitatively, we see that perhaps at small numbers of hops, 1 or 2 hops, low connectivity around nodes in the graph. We see that perhaps relational or other non-native NoSQL graph databases are roughly the same as Neo. But as you extend to tens of hops, hundreds of hops, as you extend to high connectivity, as you extend to real production-worthy graphs, where you've got billions of nodes, many billions of relationships, Neo4j outperforms because it doesn't have any of the algorithmic cost baggage that the other systems have from their primary model, because Neo4j is native from graphs all the way up. I was a little earworm that got into my ear several years ago when we had a customer in the telecoms domain who said it took Neo4j took something that their relational database took minutes to process and turn it into milliseconds. And that's simply because we've made the right choices for graph workloads in terms of the algorithms and data structures we use. Don't take my word for it. There are a bunch of popular use cases out there. For example, we have a big retailer in the US, record Cyber Monday sales, 35 million transactions at non-peak. Each transaction for their promotion recommendation engine is in excess of 3. It's typically 3 to 22 hops through the graph to make a good recommendation. And all of these queries were executed in under 4 milliseconds, which you need when you've got customers browsing your site. Ditto, large hotel chain Marriott, 300 million pricing operations per day, 10 times the transaction throughput on half the hardware compared to a relational database. And those pricing calculations required, again, 7 to 22 hops per transaction. We have the largest postal service in Europe, actually, 500,000 employees. And Neo4j routes about in excess of 7 million packages per day with peaks of 5,000 routing operations per second. And of course, routing for cheapest path, fastest path, lowest carbon path. This is a complex graph operation which typically involves more than just 3 streets of difference. It may involve typically a local urban area network, a highway system, and a second urban area network to be navigated to find the cheapest possible costs. Other folks that are doing this, eBay's conversational context-aware shopping support ShopBot. It uses a graph at high scale to understand your shopping needs and your context to give you a personalized shopping experience. And there's a company called Qualia, which, to be fair, not too many people know. It's an ad tech company, but its mission is to be able to provide good ads for you on whatever platform you're on. And in order to do that, it has to track you across all of the ways that you interact with apps and the web. So it knows that you are you on your Android phone on the train versus you are you at your Windows desktop at work versus you are you surfing from your iPad on the couch at home. And it has to be able to, in ad tech latency, join all of those facts together and then be able to give you an appropriate ad. It has about 90% of the US population in its graph. So yeah, I'm going to say 300 million people. 1 billion plus transactions per day, And it does all of this in a relatively modest 3 terabyte graph with 5 billion nodes on a very modest hardware footprint, just 256 gigs of RAM. Finally, we've got Azi Barak from Kehut Tech in Israel, and he has a Neo4j instance running with 10 billion edges and growing, good ingestion rate at 4 billion relationships per day, and so on. And all of this is possible because of Neo4j's graph native stack. So how does that stack look? Well, of course, you could read the source. Neo4j is an open source database, but let me give you the cheat sheet here. From the bottommost point of the stack, Neo4j has a graph-affine storage layer built expressly with graphs in mind, whereby we split out data and structure. That is, we store the structure of the graph separately from where we store your property data. And we optimize so that traversing the graph, going around that graph structure, is always O1 operations. So we have fixed size records for our relationships and nodes, meaning that if you know the size of a record and the ID of a record, you can multiply ID by size and you get immediately the offset of that record on disk. This is great because it means that's order 1 for each lookup, which means that if you're going to traverse through a graph, you've now got an order n problem, so you've got n order 1 problems rather than n log n. It's way, way cheaper. Of course, you know, we layer on top of that all kinds of sensible caching and so on, so we're typically working in RAM. We also have a compact pointer format, which means we try and cram as much of that graph in turn into L2, so you're always traversing the graph at the highest possible speed. On the right side, we have fast ACID transaction processing with bucketing to provide great throughput whilst maintaining safety and ordering, which are important properties to keep your data safe. On the expensive but mediocre MacBook Pro that I have in front of me, I can get, give or take, 5,000 or 6,000 ACID transactions a second through this machine. You can imagine if I had a sensible production-ready blade, you can scale that accordingly. On the read channel, we have an optimized off-heap cache, as I mentioned. We try to make sure that we run all traversals in RAM or better. And or better means our compact pointer format, which tries to give us good use of the L2 cache. At the very top of the stack, we have Cypher. Cypher is by far the world's graph query language. It's built on previous experiences of other query language and is designed to be humane and expressive. It's also very high performance. We have a high performance runtime that's aligned with prevailing runtime conditions in the graph. So our query planner and optimizer can actually take into account a bunch of graph metadata and graph structure data to make smart choices about where to run your query for the cheapest possible value, cheapest number of IOPS, cheapest number of database hits as possible. In Neo4j 3.2, we introduced a whole bunch of other things to help natively process graphs faster. We now have a compiled Cypher runtime, so that a bunch of common queries now are actually compiled into bytecode and executed mechanically even faster. We have composite indexes for query performance boost. We have a native label index. So we make heavy use of Lucene in Neo4j, and Lucene is wonderful, but it is a general purpose tool. And so over time, we observe that there are certain things that we're simply better off in the graph use case, writing our own specific index for and retiring Lucene from that piece of functionality. In 3.2, we had a native label index, and that sped up writes phenomenally. We have a phenomenal cost-based optimizer as part of our runtime and so on, and a bunch of other stuff. And our goal in Neo is not only are we coming from a place where we've built this stuff to be graph native from the ground up, but as we learn more, as more people deploy Neo, as we learn about more and more about how people run graph-based systems, we're making sure that our native implementation evolves to take advantage of that. So you'll always be on the best track. Our native graph approach, therefore, is that we've got a wonderful declarative query language, which is designed for human readability and is humane, and is extremely expressive when it comes to graphs. Our optimizer and query planner can consume graph metadata and runtime metadata into its consideration, so it can always produce an excellent query plan. We aim to work in main memory and optimize for L2 where possible, and we maximize our I/O performance. We traverse graphs by chasing pointers. That's an extremely efficient thing to do. Computers are very good at that. And importantly, all of this is done ACID transactionally. Now, often, historically, ACID transactions have meant expensive, strict two-phase locking and all that kind of stuff. Nowadays, ACID transactions are enjoying somewhat of a renaissance. We have a bunch of work, particularly coming out of the likes of Cornell and Stanford, about low contention ACID transactions, so not having to do the expensive path where it's safe to do so whilst preserving the ACID transaction semantics. So, what happens when you try to productionize a graph? What happens when you put the graph in production, or even in your lab? I think things get even trickier when you create a production-ready cluster of non-native graph tech. In fact, particularly consistency models for graphs are hard because relationships between nodes could potentially span across machines. And if you have an eventually consistent underlay, you can get to a situation where you're not sure whether certain relationships exist or not. Let's explore. There's going to be a little bit of computer science, but nothing too onerous, I promise. More formally, though, there is a design trade-off in building a distributed system between availability and reliability. And availability is the property of a system to respond to an event, accept a write or serve a read, even when faults occur. I think we all agree that that's desirable. And reliability is the property of a system to produce a correct result in response to an event, even when faults occur. And the awful thing is, for those of us in computer science or in distributed systems engineering, these things can't both happen at the same time. So there is a paper from 1985 by Fisher, Lynch, and Patterson, called the FLP paper typically, on the impossibility of distributed consensus with one faulty process. And in practice, it means that we can't have both of these. We can have a system that's available, and under pathological conditions, it will serve stale or incorrect data. Or we can have a system that's reliable, and under pathological conditions, it perhaps won't accept writes. And that's a shame, but we are forced to pick one of these. And despite marketing efforts from all sorts of folks, you can't have both. And I hope at Neo4j we're intellectually honest enough to tell you you can't have both, because FLP says you can't. Now, if you have an aggregate database, a column database, document database, kit, KV store, whatever, those databases just have to agree on a single value. And there are a bunch of different strategies for doing that. You could have something like last writer wins, or you could have vector clocks for reasoning about causality, or you could even have a totally ordered consensus protocol if you can afford it. The winning value then gets synchronized across the replicas. And you can trigger that via anti-entropy mechanisms, or you can do it like on demand on a read by doing a kind of read repair thing. You can do a whole bunch of ways of doing that. But the trade-off here is that you can be a bit unreliable. You can be a bit temporarily incorrect until your consistency mechanism makes everything hopefully eventually agree. I think that's very cool. It's enabled us in software to be able to develop some outstandingly scalable and available systems. But in graphs, we typically want to be able to traverse the relationships in two directions, which means that we need agreement of two values. That is, that we need a node that knows it has an incoming relationship from another node, and in another node that correspondingly knows that it has an outgoing relationship to that node. So we need agreement of two across the replicas. And actually, we need that to be reliable, otherwise you've got a non-deterministic graph. Let me show you the case, I think, for reliability over availability. Here we have a bit of cheeky geopolitics, and you can see that I've got graphically that Britain loves America. And if you were to try and encode that in some kind of JSON-esque adjacency list, it might look a bit like this, where on the left I have a node ID 0, country USA, and it knows that it has a loves relationship from node number 1, direction inbound. And correspondingly on the right-hand side, the node representing the UK, node ID 1, has a loves relationship to node 0 in direction outbound. And those things are reciprocals of one another, right? So that's great. And of course, we do indeed love you Americans greatly. But then what happens if you've got a concurrent operation? Well, actually, all bets are off. If the British thread is over in one side of the database updating a record that says that we love you 100%, but then the French thread is working its a way through another record and it's deleted the relationship, the question is, which one of those records is now true? And the answer is, I don't know. You're in a non-deterministic state now. If you started a traversal from the American side, you would see that the Brits love you. But if you started it from the British side, you see we no longer love America. And this is important because we base business decisions on this data. And if this data is non-deterministic, we're going to have non-deterministic outcomes to our business workflows. I mean, in geopolitics, this could even end up being in military conflict, because we rather like being allies of America, and we don't really want to have to go into bat against you. We tried that a few hundred years ago with our guys in red coats and wooden ships, and it turns out you bested us. So we figured out we won't try that again. So for graphs, reliability is actually far more important than availability. And of course, this doesn't mean that Neo is building unavailable systems. It means under pathological circumstances, Neo will prefer to stop accepting rights than give wrong answers, which actually is a little bit surprising because for so long in the database community, we have been so worried about availability and we've left reliability alone. But actually, no, I think reliability is making a comeback. And the comeback it's making on the Neo4j side of things is a consistency model called causal consistency. And really what that boils down to is, can you read what you write? Now, in any database, even the strongest, most ACID transactional, most pessimistic, conservative, strict two-phase implementation, you have cluster members that are slightly ahead or behind one another. This is normal behavior, right? Even if you think you've got the world's most consistent system, we are all still hamstrung by the speed of light. Information still takes time to propagate, and therefore changes to replicas happen at slightly different times. That's okay. What I don't think is okay is when that behavior gets exposed to end users, which so many databases, actually including older versions of Neo4j, did. And it manifests itself this way. So here I am, I've got an app and I need to log into purchase, but I don't have an account yet, so I'm going to register. So here I go to the registration screen, type in my details and my super top secret password, and then I'm presented with my login opportunity, fill in my username and password, and what do you think happens next? Fail. What? Okay, this is annoying because it's a username and password thing. Maybe I take my business elsewhere, I don't know. The thing that really bothers me about these kind of situations is where I just put $100 in my bank account and then I go to read my bank account and the $100 isn't there, because that feels like I've lost money. Of course, I'm somewhat confident that the bank are reconciling that in the background, but it really doesn't give me a good feeling when I think the bank have just immediately lost $100. Of course, on retry, I might find that my login was successful. So why didn't that work out nicely? And the answer is because of eventual consistency. The user of the app transitively was connected to the semantics of the database. And actually, this is one of the lesser evils of eventual consistency. There are other worse evils like replica diversion, visibility of uncommitted values, and all sorts of stuff. But sometimes it scales well. So pick carefully is what I'm saying. But in this case, I think the end user being given an eventually consistent answer is simply not good enough. In Neo4j, we have introduced in Neo4j 3.1 this notion of causal consistency. Because we're a transactional database, a transaction is effectively, you can use it as a version of a database. So you can perhaps say, when you make writes to the database at version 10, when you later go back to read from the database, you're now able to say, hey, the last version of the database I saw was 10, so please only run my query if you're at version 10 or beyond. And we call that thing a bookmark. And bookmarks are baked into both the Neo4j cluster and they're baked into the Neo4j drivers. So all of this is mostly transparent to the end user. So we can now build a system with this causal consistency, and let me show you how that works. So this time we're going to create an account. We're going to throw some, our app talks to an app server, which talks via a Neo4j driver, which then talks to the database, and some stuff happens in the graph. In this case, I've got a majority of my machine's accepting the write using the raft protocol actually, and then we return to the user. In this case, we're carrying a bookmark with us, so we're round tripping a bookmark through the user. Could be a cookie, could be a URI query param, that kind of thing. Now, when I try to log in, what's going to happen is I'm going to pass that bookmark along with my login request, and notice in this case, record 11, which was the create account record, isn't present in this database, neither in the log nor has it been applied to the end model. So what's going to happen here is actually the database is going to just stall for probably a few millis while the replica receives that data, and then only once that data has been applied to the log and ultimately to the model will the query run, and then the query returns, and this time you get login successful. So this isn't like super rocket science. This is just taking advantage of one of the affordances transactions gives us to make sure that you never go back in time, so that your graph data always is at the very least at the same state the last time you saw it. You never go backwards. It gives you bounded staleness characteristics. So this is how we create the account. This is how we read it. And actually it gives us a really nice pattern for reasoning about graph data. It actually gives us a really nice pattern for reasoning about data in general. And I think that fault tolerance must respect the graph. And so Neo's approach with ACID transactions implies no corruption by design, and compared to others, which can provide corruption under non-fault operation, where you've got diverging replicas because of eventual consistency. Our replication model also maintains high performance pointer chasing, so it still gives you excellent query performance because we don't do over the network traversals. All future versions of Neo4j will honor this as well, even as we evolve the fault tolerance and network cluster protocols. And even when we choose to split Neo4js over the network, we have the lab work to demonstrate how that can be done also very efficiently. So let's talk about native again. Ultimately, this is about graph native. So let's talk about what happens when we push Neo4j to its limits. The results are pretty interesting, actually. So my CTO, Johan Svensson, is a very low-level kind of Neo4j kernel hacker, and he built a benchmark for internal consumption that I'm going to share with you. And we took a realistic retail data set from Amazon. We took a commodity dual Xeon processor server. Actually, nowadays it's not even commodity. It only had 512 gigs of RAM. And Johan, being a low-level hacker, wrote a Java procedure, but it was equivalent to this cipher, where it's like, hey, database, find me a pattern where I bought something that someone else bought, and tell me a recommendation that they bought. And of course, that's a very straightforward peer pressure kind of recommendation technique, where I get told something that someone like me bought. So if I buy an iPhone, and then you bought an iPhone and some wireless headphones for the convenience of wireless or something, then I will also get recommended wireless headphones. And what Johan found was on a single thread, you could get about 3 to 4 million traversals per second. With 10 threads, it goes up to nearly 30 million. At 20 threads, it goes up to 50 million. And asymptotically, at 30 threads, we got about 60 million traversals per second. That's best in class on traversal speed and scaling up reads. He also discovered in this that Neo4j can quite comfortably handle 1 trillion relationships on a single server, 33 terabytes out of 48 terabytes used on disk. Neo4j's actual addressable space is many quadrillions. And in doing these kind of queries, when we then ran a compiled cipher query for random reads, we found that we could sustain over 100,000 user-level transactions per second. And that's really important, right? Because with only 512 gigabytes of RAM compared to 33 terabytes on disk, we could still do 100,000 user transactions a second, even when most of the time we have to go down to disk to get data. I think that's pretty amazing, actually. And that's not a celebrity endorsement from Professor Brian Cox. In terms of writes, we imported the Friendster data set. It's about 1.8 billion relationships. Takes about 20 minutes. That's about 1 million writes a second. And thanks, Brian. That's very good of you for not giving us a celebrity endorsement there. Even on my modest laptop, for non-ingest scenarios, so for ACID transactional scenarios, as I mentioned, I can get 6,000 ACID transactional updates into my graph per second on this laptop, which is nothing special. Take my word for it. But let me call that out in big bold numbers. Neo4j can do 1 million writes a second. It can hold 1 billion records quite conveniently, and it can do 50 million traversals a second. These are some pretty big numbers, all because we've chosen the right algorithms and data structures for graph workloads. So if we can compare that, there were some guys on the internet who've got a non-native graph layer that they sit on top of Cassandra, and they published some benchmarks. And these were great benchmarks because they showed an improvement over a previous release. When I saw these, my interest was piqued. Oh, actually, I wonder what Neo4j would do for these. So this is a big beast of a cluster they've got here. So they've got 6 machines, each with 48 virtual CPUs, 256 gigs of disk, 256 gigs of RAM. So that's quite a lot. So it's about almost 300 cores, 288 cores, 1.5 terabytes of aggregate RAM across these 6 machines. That's huge. The data set that was used here is that they used was a synthetic 10 million node, 100 million relationship graph. I didn't have access to that data set, but I did take the DBpedia data set, which is comparable in size. It's 11 million nodes rather than 10, and it's 116 million relationships. But order of magnitude, Neo4j's test data was only about 10% bigger, so within bounds of experimental error, I think. Now, when we ran the same algorithms in Cypher on Neo4j, so Neo4j out the box on Cypher, no fancy tuning or anything, it was outstandingly interesting. So for count nodes, so counting number of nodes in the graph and counting number of relationships, Neo4j was at least 200,000 times faster. I don't know exactly how much faster it was because I only set millisecond precision timing on these experiments, and it said it took 0 milliseconds. Now, when I told my engineers this, my fellow engineers at Neo, they said, of course, that's the case because that's cheating. And I'm intrigued by this. I said, what do you mean by cheating? So, well, when Neo4j counts nodes or counts relationships, there's a specialized store for that gives that answer immediately. I'm like, okay, so it's not really cheating. It's that we've understood these are common graph operations, and we've adapted our native graph database to uphold those operations, to execute those operations very rapidly. So because we've got a native store, we can evolve that to do these kind of things. So yes, we are 200,000 times faster than a non-native store in this case, and that's because we've made our store native for graphs. Count outgoing rels at depth 2, we're about 10 times faster. Count outgoing rels at depth 3, okay, we're not extraordinarily much faster there, but we're still 20% faster. Count group nodes by property value, so selecting a bunch of nodes based on the existence of some property value. We're about 20 times faster. Group nodes by rel type, 4 times faster. Count depth 2 knows like, so a pattern where I've got someone that knows someone that likes someone, twice as fast. And I think the acid test, if you'll forgive the use of acid in a different context, PageRank, the classic iterative compute-centric algorithm, 1,000 times faster. And moreover, all except for the asterisk executions will run on my laptop. The ones with asterisks run on them will run on my colleague Michael Hunger's desktop because it has a bit more RAM. But Michael Hunger's desktop, I believe, has 128 gigs of RAM. It certainly didn't have 1.5 terabytes of RAM and 288 cores. It was a single core, single thread on 128 gigabytes of RAM. So kind of, fancy pants desktop maybe, but certainly underpowered in terms of production hardware. And the native graph operation still beat this non-native solution phenomenally. So if you're a fan of Silicon Valley, as I am, I'd just like to say one more thing. It's all very well having this amazing technology, but it's no good having it if it's made inaccessible or impenetrable by its interfaces. Neo4j and others have the Cypher query language, the most advanced graph query language produced so far. It eats complexity for breakfast in a way that SQL and other languages don't. So when you're thinking in graphs, you don't want to have cognitive dissonance. You don't have an impedance mismatch between the picture you've got in your head, the sketch you've got on your whiteboard, and the way that you have to express it in your data model and in your query language. It pays to have a language that supports your query mental model. OpenCypher has extended its reach now. It's on other databases, it's on Neo4j, it's even on Apache Spark. And I think it's plain to see that in this query, where I'm looking for where I live in the corporate hierarchy, the Cypher on the right is accessible to those of you who even haven't seen Cypher before today, whereas the SQL on the left, you have to be a special kind of relational aficionado to make sense of that. And I, for one, am not volunteering to debug and own and maintain that code because it is nightmarish. So let me recap. Why should you care about GraphTech? 1, performance. Native GraphTech is blazingly fast for graph workloads on commodity hardware. Native graph tech, Neo4j, keeps your data safe. We don't compromise graph data with weak consistency models, which are perfectly fine for other data models, but not good for graphs. And in terms of usability, you've got faster time for value, ease of evolution. You are not hamstrung by clunky other data model schemas and so forth. And you've also got better ecosystem tooling. So you're going to get all of that benefit from people that have trodden the graph path before you, rather than having to learn from a community whose preference and whose heart, frankly, is in other models. Wonderful. Thank you, everyone. Thanks for your time. Bye-bye.